Let's learn about matrix rank. This is extremely important because you will find this in all of the matrices, and this tells you how much information matrix contains. So in your neural networks, in your large language models, when you have any kind of matrix, there is so many different kinds of matrices, you can actually maybe approximate those big matrices with small matrices, so you save on computation. So rank of the matrix will tell you how much unique information this matrix holds, and the lower the rank, you can use smaller matrix to approximate this big matrix, and this is extremely important, and you will use it. Here in this matrix we have 3 columns, but you will notice that the third column is just the sum of the first 2 columns. So we only have 2 linearly independent columns, while third is dependent and it's redundant and it doesn't add additional information to this matrix. So this matrix has rank 2. In this other matrix, here row 3 is just equal to row 2 minus row 1. So row 3 is not holding any additional information, it is dependent, while these 2 are linearly independent. So the rank here is 2. So we can say that this row is useless because it doesn't provide any additional information. And so if this was your matrix for a neural network, you could actually just use 2 of these rows or create a smaller matrix that's going to approximate this matrix, that's going to in some way keep this information while discarding this information. It can be done in different ways because this information is just redundant, it's repeated. So if this was your attention matrix, for example, attention scores or weights, this you don't need to do. This would be unnecessary wasted computations. So for any matrix, the column rank is always equal to the row rank. This is why we can just call it the rank of the matrix. And what does this rank mean graphically? So you know that when you use a matrix to multiply a vector, it will rotate that vector. So let's say you have a 3D vector, and this is explained well in 3 blue, 1 brown matrices, linear algebra. So you have a vector, multiply with a matrix, it will just rotate vector. So let's say it's a 3 by 3 matrix, but let's say the matrix has rank 2, okay? So rank 2, if it's not rank 3, which is the full rank, so rank 3 would just rotate or stretch or squish. But rank 2 would squish one entire dimension, and now it will become just a 2D vector. So it will destroy a dimension, and you will not know what that dimension was previously by just looking at the 2D vector. You don't know the number for the third dimension. So it kind of destroys information there. When you multiply this 3D vector with a matrix that has rank 2D of 2D, rank 2. And this is well animated in 3 blue, 1 brown video about matrices. Rank 0 is a good matrix to visualize. So you have some vector, and because whatever matrix we have, it needs to follow the rules of mat-mul matrix multiplication. So these rows need to be equal to these columns. But what I'm trying to say is now you multiply every dimension here with 0, so it will just squish entire 3D vector into a single dot. So remove all of the dimensions, and now it will just be at 0, 0, 0 at the center, single dot. So it will destroy all of the dimensions, this matrix with rank 0, which is the 0 matrix. This is a 0 matrix, it's all zeros. Join my school to become AI researcher. These are all of the courses we have. It's free for now. I'm gonna make it paid, so hurry up, link below the video. Same goes for rank 1, it would squish the vector onto a single line, just one dimension. And so some rules, if you have matrix that has m rows like this and n columns, the maximum rank that matrix can have is whatever is the smaller number of rows and columns. But it can also have lower than that. So the full rank matrix would be whatever the number is smaller, number of rows or numbers of columns. And matrix is invertible only if it's full rank matrix. So as I explained earlier, when you have a 3D vector and you multiply with rank 2 matrix, it will destroy one dimension, squish it to a 2D plane. And there is no way to know which dimension it was and what the value was. So you cannot invert that operation back to 3D. You don't know what the dimension was. So it's only invertible if it's full rank. If it's not, so you look at the matrix itself. You don't even look at what vector it multiplies. So if 2 by 2 matrix or 3 by 3 matrix, it doesn't matter which, we are not looking at the vector it multiplies, just looking at the matrix. And so if it's full rank, it's invertible. So only square matrices can be invertible, or should I say invertible. Let's follow an example. Let's say we have a vector and it's just 3 numbers in the vector and we have a 3 by 2 matrix. So if we multiply 1x3 times 3 by 2, we get 1 times 2 vector at the end. So only square matrices can be invertible because in this case we destroy one dimension, so we cannot get back. We don't know what the dimension was. And I'll show you one more example. So 3 by 2 matrix times 2 by 4 matrix. We can just see the ranks. So the rank of this matrix is 2, the rank of this matrix is maximally 2. So maximally 2 and maximally 2. So, and then the rank of the resulting matrix is gonna be the smaller rank of those two ranks, so it will just be 2. So that means that when I multiply these two matrices, even though the result will be 3 times 4, all of those dots will lie on a 2D space because the rank is just 2. So it says here the transformation did not create a dimension of information, it just presented 2D information in a 3D format. And one analogy would be if you have something drawn on paper and put it into some 3D room, that information on paper is still in 2D. Which then means that in this 3 by 4 matrix, only 2 rows and only 2 columns are linearly independent, and others are dependent on those two. So we can have column 1 and column 2 independent, and then column 3 being some number times column 1 plus some number times column 2. And column 4 can also be linearly dependent on these two other columns. And for rows, because the rank is 2, so rank is 2 means for rank for rows and rank for columns is same, always same. So the third row will be linearly dependent on it will be some number times row 1 plus some number times row 2. Join my school to become AI researcher. These are all of the courses. It's free for now. I'm gonna make it paid, so hurry up. Link below the video.